Log on, tune in, find out. Another good idea from Cambridge.
Our next speaker is Tobias Mielke from Universität Magdeburg, and many of you have heard Tobias's presentation last year at MODA about approximation of Fisher information metrics for nonlinear mixed effect models, and I think that Tobias will elaborate on that presentation and present new results. Please.
So now I have to present new results, I think. Thank you very much, Basher and Sergey, for this really nice conference. It's a pleasure to be here, and I really enjoyed these talks up to here, and I hope you will enjoy the talks following now as well. So what Sergey said, last year at MODA I was presenting some approximations to the Fisher information. In fact, there were just some considerations on two approximations which are often done. And here we will have some further approximations to the Fisher information. And we will see at the end that they will just collapse back to something which is unfortunately already known. But as I'm from Magdeburg, and in Magdeburg the nothing was invented, I will show you as well how from nothing can information be invented. So enjoy the talk. So we will start with a little review of the things we did, for example, at MODA last year about these two approximations which are really often used. There we'll have the first example. Then we go on to some design stuff, and we'll make a second example there to show that the information really matters. And then we will go on to the third part, where we have some information approximations, where we motivate the information approximations with another way. And then we'll have a third example, and we will return to the first example. One more question to the native English speakers. Are there any other words one can use instead of approximation? It seems to be used so often, and I don't know already in my thesis which other words I can use instead of approximation, so please tell me.
Evaluation. Not exact.
Evaluation is...
Not quite.
You will find yourself only to 3 examples, so you will go further on and consider example 4.
It's something like example 4, but
I just like your presentation. Example 1, example 2.
there are other things than examples as well, but I just wanted to have them in this so that I can click somewhere there to go quicker back to the points where Basha will have her questions probably. So my first slide is always like this. So we have these 5 concentration time profiles of some individuals, and we assume that these individuals are taken from a big population, so that we can assume these individual parameters as realizations of random variables, what leads us to the mixed effect models, which we define in these 2 stages. So first, this intra-individual variation, where we know the response function, but we don't know for sure the individual parameter vector. And we have these epsilon ij, the observation errors in the j's observation of the ith individual. And these I assume to have 0 mean, variance sigma square, and we assume just these homoscedastic structures. So we don't have the structure as Sergey had in his last talk, because this makes things already hard enough. So why should we take now additional problems here when we have already these problems for this relatively simple model? So we assume just this structure on the second stage of the individual parameter vectors. So they are realizations of a random variable with some fixed mean, which we don't know, which we wish to estimate, and some random variable bi, these random individual effects, which have here the variance sigma square d, and d is assumed to be positive definite. Individual parameter vectors and observation errors are assumed to be independent, and this is another restriction of our model. We assume that sigma square and d are known. It's just for simplicity, so that we don't have to look at the whole information matrix, but we want now just to look at the part of the location parameter beta. So our aim is the estimation of beta. Some more notations And the whole observation vector yi can then be described as the vector valued response function iter, now here of the mi experimental settings, which are here given with the individual experimental design xi. And this is something as our design matrix is just the Jacobian of the response vector valued response function. And this beta here denotes the place where we in fact evaluate this design matrix. So there might be some beta naught if we have some guess of beta or beta I instead. When we go now, yes, we want to estimate this parameter beta. We want to optimally estimate, so we want to minimize the covariance of some estimate beta ahead. So in fact, with these limited numbers of observations per individual and the limited number of observations in the whole population, we have a problem that we usually don't know the covariance of these estimators. And usually for unbiased estimators, we then use the inverse of the Fisher information matrix as its lower bound for the optimization of the designs. But that's the problem here in nonlinear mixed effects models, that we can't express this in a closed form representation. So what's often applied are these linearizations as we had it earlier in other talks already. So there are two possibilities to linearize the model. The first one is some linearization in a guess beta naught of beta, or maybe even of beta I, the individual parameter vectors, and then we come to a linear mixed effect models. It would be something as, for example, in the pseudo data set of the Lindstrom-Bates algorithm. If we take here the mode of the penalized least squares, the solution of the penalized least squares problem. The nice thing about this representation is that the variance matrix of this approximated model doesn't depend on the true parameter beta, but it depends on the guess beta I or beta I hat or beta naught here. So it's just linear mixed effects models. Another often used approximation is just to linearize the model in the true population mean without knowing it for sure, but we can assume that we linearize it. So then we have here this term inducing the variance. So this is nothing more than our random individual effect bi. And here we have our observation error vector epsilon I. So we get a heteroscedastic nonlinear normal model because this variance matrix v beta depends on the unknown parameter vector beta. And for the information matrices now, for the computation of the information matrix, what is often done is we assume that this approximated model by these linearizations is a true model. So we have the true model, we think. From this true model, we take the score functions, then we take the expectation of the product of the score functions, and then we get the Fisher information matrices or some approximations to them. And these look in, there are different ways to do this. With the first thing, this linear mixed effect models, something what was done, for example, by Ritou and Montré, and I think Steve Tefalio was included in this paper as well. It was the development and interpretation of the Fisher information. Then we get this form. 2 years later, there was a paper published where there was some additional information which was coming logically here from this sigma square v beta, because it was assumed that we linearize in these true parameter vector beta. So we have this nonlinear heteroscedastic information, what was used by Sergei as well. So here we have this non-negative definite extra term, matrix term S here. So as a little example, assume we have this log normally distributed random variable and a normally distributed random variable here. Then the first information matrix looks this way. The second information matrix looks this way. So that's the additional term. And what you see here is just the ratio of these two. It's a parameterization of this variance d by, I think it's rho divided by 1 minus rho, so that you have the whole real line just in this interval of 0 to 1. And if you see as the variance of the individual parameter vectors increases, the information of the second approximation increases as well, so that that in fact when we have really huge individual variances, then we get that the second information matrix, this nonlinear heteroscedastic information, is much more better than the other one.
What is rho here?
Rho is d1 divided by 1 plus d1, with d divided by 1 plus d, so.
What's the y-axis?
The ratio.
The ratio? I didn't see it's a ratio, it's a difference.
No, it's a ratio, it's a ratio.
Ratio of which one?
It's m1 divided by m2, so the linear mixed effects information divided by the nonlinear heteroscedastic information, because when we would take it otherwise, there would be something going to infinity, so we have it constrained on the interval from 0 to 1.
And which curve is which?
Hmm?
And which curve?
Okay.
What
Yes.
curve
Sorry. I didn't say that.
Yes.
So we have these 5 curves. So this is just for different values of the mean beta. So this is for beta equals -2, -1, 0, 1, and beta equals 2. So it depends on the mean of the individual effects. That's the thing. So this is the example we will where we will go back to at the end of this talk, and there will be these 5 cases from -2 to 2 as well. But right now we will go to the design of these experiments we have here. So experimental settings I here assume to be some, we assume on the individual level some exact experimental designs, so that we have per individual some mi observations, and we just have this vector of these individual experimental settings with the xij from this design region X. Alternative would be the use of approximate individual designs, as Valery mentioned yesterday. I think what he said wasn't really so right, because he said this is something just this is something what should be done only by PhD students. But if you take your designs just as benchmarks for your real designs, you might take these approximate designs, because Thomas Schmetterl has some optimality results for these approximate individual designs, which might be used somehow to as benchmark for your designs. So that's a motivation why one can use them, but they're for sure not realistic in these studies. So the populations designs are here nothing more than an approximate design than on the design space, m-dimensional design space, when all individuals have the same number of observations, what we assume here, such that design optimization leads back to something what is already probably 50 years known. So it's just this equivalence theorem for d-optimality, for example, which was stated in the works of Valery Fedorov, 76 or 72, I think it was. Yes, and so for this multivariate case, so we have where we have this inverse of the population information here, and here we have the individual information, and when this term, when this guy is smaller than p for all individual designs xi, then we have a d-optimal design. Similar things hold for some linear criteria, so it can be done with your 3 wheels and everything is fine. The efficiency here is with delta, we will here denote the efficiency, and we just talk here about d-optimal designs. We don't want to make things complicated, we just want to concentrate on some little problems. Yes, the summation here we already had in your talk, Sergey. It's just because observations of different individuals are for sure independent, so that we can sum up this information matrix, so no problem. And then I had this for the preparations of the last conference, which was held here 3 weeks ago. I had a look at the dissertation of Thomas Schmelter from 2007, because I was looking for some example, and I wanted to know whether these 2 different information approximations, this nonlinear heteroscedastic and the linear mixed information, whether they how the design looks like in some more complicated example. In fact, this was this paper you mentioned already by Merlet and Todd, where they said that the information matrices has no big influence on the design or something like this. I think it can be this way summarized. It's an interesting paper, yes. So you have here, we here assume a one compartment model with first order absorption and proportional errors as log normally distributed and multiplicative. And we assume that these individual parameter vectors are proportional as well. So what one now does is one takes the logs concentration, then we have additive normal distributed errors, and one somehow transforms this expression so that we have some additive random individual effects instead of these multiplicative. The individual, these parameters, clearance, volume, and elimination rate constant are here assumed to be independent of each other, but it's the absorption rate constant, I think. So, and then I took Valerie's three wheels and computed the optimal designs for both information matrices. So the first optimal design, it's the one in the linear mixed effects models approximation. And that's the optimal design in the nonlinear heteroscedastic model approximation. So, and as you see here, this optimal design in the nonlinear heteroscedastic model approximation has, in terms of the linear mixed effects information, just an efficiency of 0.66. And otherwise, the first design has, in terms of the second design, just an efficiency of 0.55. So they're really inefficient. And in fact, you can see this relatively easy. These are the sensitivity functions here plotted, and they are a little bit transformed so that they are beneath zero everywhere when the design is optimal. So with the design theta 1, we would have the observation at 0.1 and at 4.18, which are somehow very close to minima of the sensitivity function of the, in terms of the second information. So what we have here is just that we observe at the somewhat the worst points where we might observe. So these are one-point designs. So we have one observation per individual. Sorry, I didn't mention that. One observation per individual. Yes, it's a very small individual sample size, I know. So information matters, and we will have to have a look some more into this whole stuff. So once again, we have this nonlinear mixed effect model with the response function ether and the distribution of the individual parameters and the observation errors. And we can write all this thing in some kind of closed form, but we cannot calculate the integral which he goes on the per-dimensional real on the real numbers here. So the problem is the nonlinearity of the function eta here. L tilde will in the following describe these penalized sum of squares. And we want to have some insight in this guy. So what I was thinking about is just at first doing the differentiations and so on, and afterwards looking inside the approximations. So it's relatively easy to see that the score function is nothing else than this term here. So some conditional expectation of the parameter vector beta I for given observations yi minus the true parameter vector beta, such that the whole information matrix can be represented in this form. So the variance of the expectations and the expectation of the variances. And these sigma squared d, it was the real variance of the individual parameter vectors, which is assumed known. So in fact, everything goes to approximation of conditional moments. Probably we can give this problem to some Bayesians and they will solve everything without problems, or not. But so what Valery said, if we have some other parameterizations of the individual parameter vector, if we have some function g of beta plus some random effects bi, then everything holds the same way, just now with the Jacobian in front of all these terms. So that's no problem. What one might do to approximate these conditional moments, usually some quadrature rules as T to n, and or some simulations, Monte Carlo based as Sergey did. These are probably these are methods which might be applied, and they for small parameter, small dimension of the parameter vectors, and for small numbers of individual observations, they might really possibly rather well work. But if we have a big dimension of the individual parameter vector and so on, then they will get probably computational intensive. The more, if we want to have some insight in the dependence of the design on the information matrix, so then we would have to have a lot of different time points where we wish to observe this information matrix. Another thing what is sometimes applied to approximate conditional moments are the Laplace approximations. And that's the thing I wanted to look at a bit. The problem is there might be the accuracy, but we can get maybe some closed form relationship of these, some closed form relationship of an approximation of this Fisher information. So the problematic guy in all this information matrix is this product of the conditional expectations. So I had a look at the expectation of y given beta I, and there was this paper by Tierney and Cadane where they approximated conditional expectations of some positive functions by approximating the denominator integral and the numerator integral by Laplace approximations. So in fact, if there are not positive function beta I dimensions, that you can just add some really big constant to your function and then do the same stuff, and afterwards you subtract this big constant again and everything works fine. That's what they said in the paper 2 years later, I think it was. So this might be done, but it isn't satisfying. So the problem is we have then this dependence of yi in our mode of these penalized least squares problems. So in the Laplace approximation, what one wants to do is one wants to approximate this the whole integral by approximating the integrand with a second order Taylor approximation of this penalized sum of squares in the mode, so that these points where a lot of information is, so that we will have these points well approximated. Then the linear part vanishes as we have the mode, so the first derivative is 0, and we get some normal density in the integrand, and then we have this approximation to the probability density of the observations yi, where this C2 is some kind of constant, which yes, it's constant, but it depends on the value of yi and the value of beta, so it's not really tractable here. And as I said already, our problem is this dependence of the mode on the yi. So what we did, in fact, we just looked at this conditional density for given observations yi, and we applied a similar approximation. In fact, we applied the same approximation as we did to the numerator to the denominator. Yes. So then we can approximate this conditional density of beta given yi by a normal density with mean beta I star. So this would be the mode, and m beta I star. It's a variance. It's here the Hessian of this penalized sum of squares term, and still we have the problem of the dependence of the mode on yi and of this matrix on yi. So we haven't solved this problem. And maybe there will be some ideas to solve this problem later in the talk of Joachim Nieberg, because he's doing something on first order conditional estimation. So maybe there will be some more insight. I don't claim in no way that this thing is normally, that this is a normal density. This won't be a normal density because of the nonlinearity of the function eta. So another thing to get rid of this dependence of yi would be just to linearize this function eta beta I xi in some point beta I hat. So it don't have to be necessarily the mode, it can be just some beta I hat we take here. Then applying the same approximation to the numerator, then we get this form. So we have some mu as the expectation and some sigma square m beta I hat as the variance, and with this we might get some closed form, but in fact it might be, as well as every other approximation might be a bad approximation. So we use an appropriate choice here of beta I hat, and the first choices one would use is either this, again, this penalized least squares solution. Then we have something similar to the simulation we had earlier, but now with this m beta I hat. Note that this is the same thing, just as the Hessian of this, the penalized least squares function, just with one term missing, and it's the term of the second derivatives of the function eta here, and the difference of yi and eta. So, and another choice, so here we still have the problem of the dependence on yi, so nothing new. Other possibility is just to approximate around the real value of beta, the real population mean beta. This might be done, and then we have some closed forms of the approximation then. And a third thing, which I was thinking about just when preparing the presentation for the last conference, and I don't know why it didn't came to my head earlier. So it's just an approximation around the true parameter beta I, without knowing it for sure. For the first thing, for this approximation in the true population mean beta, we then get something what we already know. So this is the approximation of this is the true Fisher information, and this is the this formula which has the conditional variance in there. And if we take the conditional variance of this approximation, it's a sigma square m beta inverse, we will get with some matrix inversion formulas just to this thing which we already know. This was our first approximation we had. It's just the linear mixed effects approximation. So it's nice other motivation how to get there. Second thing would be the approximation of this conditional expectation. Then we get some term which is more complicated, and in most cases even not possible to write down, because you usually don't have a closed form of this variance of yi. Straightforwardly, one might just approximate this by this linearized thing. Then we come back to this m1 beta again. So this will be denoted by m3 beta. Two other approximations. Here is the one with the real beta I, but then we would have some, so to make this tractable, we take the expectation of this, so the expectation over the beta i's of this whole matrix. Isn't computable as well, but we can use simulations, as did Sergey in his last talk, to get nearer to this problem. And just to remind you, there's still this nonlinear heteroscedastic information which might be considered, and there's this quasi-information. When we know the expectation and the variance, one might just approximate the true information with the quasi-information, and this would be the Jacobian of the expectation of the observations yi, and this is the variance of the y, the variance, yes, the true variance, inverse of the variance. So here, a short summary. These are these 5 which we will consider in the following. In the next example, we'll especially just consider these first 3 and the last one, and the m4 beta will just appear in the last example, then in example 1 again. So we had this example already last year at MODA, I think. We have just this log concentration again, just one observation per individual, and we have again proportional errors, proportional random effects, and random individual effects, and we just rewrite this whole model so that it is in form as we described our nonlinear mixed effects models. And we wish to optimize the design on the design space of some interval, T min, T max, some time interval here. And that's the way the information look like. So it's the information matrix, of course. So that's the information for beta 1. That's the covariance of these 2 components, and that's the information of beta 2. So the black points are simulated values for the true Fisher information. The red curve is the linear mixed effects information. The blue curve is the information of the nonlinear heteroscedastic model. The yellow one is the information with this conditional expectation it was. And the green one is the quasi-likelihood information. And you see that this linear mixed effects information seems to work reasonably well. If you would take now the this fourth approximation with the expectation of these beta i's, I made this once, it somewhere is still some closer to the true information matrix here. But as Basha mentioned at the last talk, she asked, how does this all depend on the variance of these individual effects? And it depends for sure on the variance. Thank you. So we will have later another example where we see a little bit of the variance if I go fast enough. So to get the optimal design here, it's relatively easy for the first and the fifth information, so the linear mixed and the quasi-likelihood information. We just have to take observations x1 and x2 with half weight on each, which are solutions of this this equation, and if there are no solutions, then we just take the endpoints, T-min and T-max. This can be easily seen if you just write down the sensitivity function. I like analytical solutions, that's why I did this. So that's the sensitivity function for d-optimality. M is here 1. And you just take now this matrix A, B, B, C, what you assume to be the true population, the population information here. And then you write it down, and you see then that you will have just two superpoints, because this will be a second order polynomial, and that you might take a design with two superpoints and weight 0.5 at each, and at the end you get to this formula for this sensitivity function, and either this is 0 and everything will be 0, the whole sensitivity function will be 0, or we take the endpoints. If we don't take so, this will be always greater or equal than 0, that's the problem. If you don't make it this way, we'll have problems as somewhere there will be a point to the left or to the right of these x2 and x1 where this function will be bigger than 0. So that's a problem. So in fact, this has to be 0 such that the function is 0 on the whole design space and everything is fine. It's a similar thing to that what Reiner did with this linear regression with one observation per individual, but won't go further into detail. So these are the information matrices, and Eugene Demidenko's story here, or
left.
Oh, because here we have again this problem that we have always some high efficiency now here. So not as in the last example. So it doesn't really matter which approximation we use in terms of the linear mixed information. They all yield a high information. We took for this optimization problem, we took the 3 wheels of Valery again. And now to the next example, to the first example, back to this. So these are our information matrices. The simple case of a log normally and a normally distributed random variable. And you see already here that this information based on the conditional expectation is something not very nice, but it's handleable. And you have this as the quasi-likelihood information. And again, we did some simulations, and we simulated the other information as well, this with the expectation of the beta I then. And that's what we got for n equals -2. So the black line, it's the linear mixed effects information. The dotted line is the quasi-likelihood information. The dashed line, it's the nonlinear stochastic information. And the dot dash line, it's the conditional expectation information. And the blue one, these are the simulated values for the information in this beta I values. And the red points are the simulated values for the true fish information. So as you see, they approach, most of them approach here 0, just these two don't approach 0, and here they are all close to each other, and this should be this way. We'll see later.
Can you remind what rho is? Rho.
Rho again, yes, rho.
On the left.
It's on the left. It's written on here. It's the ratio of it's d divided by 1 plus d. It's just the variance divided of the individual parameter vectors divided by 1 plus the variance of the individual parameter vectors. It's just to make the whole things, just to show it all on the interval from 0 to 1, because we don't want to see this on the interval from 0 to infinity without knowing where infinity ends. It's not 9, I think. Infinity is 9. Yes, this same thing can be done for the other values we had, for -1, so everything moves a bit to the left. For 0, then for sure this linear mix information is just a straight line. For 1 and for 2, and here you see already this information based on the conditional expectation of something which isn't working because the variance term in the middle has some exponent which is going very quickly up to infinity, and so just forget about it. And it has an explanation why it doesn't work. I think it was Tierney and Cadane saying that this approximation with the approximation of the expectation is worse than the approximation of the variance, or something like this. And this dotted line here is C, and that's the thing I wanted to tell you at the beginning. You see, that's the information of the nonlinear heteroscedastic model. So in fact, we are here with the true information, we approach 0. It will be 0 for infinity, d infinity, whereas the information of the nonlinear heteroscedastic model has as limit 2. So we construct some information out of nothing, so 5 minutes left. Great. Yes, so just to explain this now, for d to infinity with this whole thing, you can see that the information will go to 0 because we have infinity divided by infinity square, and infinity divided by infinity square will be here in this case 0. And for d to 0, sure, everyone knows it, so we come back to some nonlinear regression problems. So this will be just this 1 divided by sigma square f beta transpose f beta, and then all informations we had will just coincide, so it's no problem as well. For the rest of the behavior, I don't have a big idea yet what happens there, and I'm still thinking about it, and probably I will think the next week in holidays about it, because I can't stop thinking about it. I have to finish my PhD. And yes, so conclusions and outlook, we got another motivation of this model approximation by linear mixed effect models. We saw again that different information matrices yield different designs, and we saw in this example that there is a big influence of the inter-individual variance on the accuracy of the approximations. And for further work, I think there's still a lot of more insight needed in the appropriateness of the approximations. And this thing here, the approximation in the mode of this of the integrand will be interesting as well, and I hope we will hear much about this in the next talk. And a third thing is, for sure, we're just looking right now at the location parameter, so it will be interesting to see how everything works when we include the variance parameters. And I thank you very much for your attention, and if you need further information, then please ask me.
Perfect timing. Thank you very much. Any questions, Tobias? Please.
Coming from a background in nonlinear regression, the way that I think of the nonlinear mixed effects model is that you're going to begin with the nonlinear regression model, and then you're going to start moving the parameters around. And so you have this basic assumption that you're going to get, underlying is always a linear approximation. You know, as I move the parameter, yes, I'm going to move the fitted, I'm going to move the true parameter value in a linear way. And for that to be reasonable, you've got to look very, very carefully at your parameters. Now, I suspect that if you change the parameterization of the nonlinear model, so instead of looking at the volume distribution, you look at the log volume of distribution, yes, or something like that. And again, that's going to affect your assumption on the mixed effects. That's one of the things that's different about mixed effects model than a nonlinear regression model. When you have the nonlinear regression model, you can transform the parameters and you have essentially the same model. It's just whether or not it's convenient. Whereas if you go to the mixed effects model and you transform the parameters, then you're changing the distribution of the random effects. And
Yes, I know.
so you have to be very careful about what you're using as an approximation, because frequently these things will not end up looking linear close to your presumed value set. You know, I think basically what's happening is that the linear approximation and the Gaussian distributions, which are nice and symmetric, they end up, you know, all these extra terms keep canceling out on you. And as a result, you know, you come back to the linear mixed effects, looks okay in many cases. If you start to increase the variances on the random effects, then you're just taking big jumps in the parameter space, and your linear approximation is breaking down.
Yes.
So, I don't know that it's easy to look at the local approximation. I think the way that it's going to come out is in the simulation.
Probably, yes. It's
Yeah, because the linear approximation is just going to have too many things that drop out of it. You know, you're interested in the high order terms, and you're dropping them out.
I agree with you, but it's just we wish to have some insight in the experimental settings on the information matrices. That's why we need some approximations, and the simulations they might get some approximations. So, for example, in this example 3, where we have the simulated values of the information matrix, there you can relatively easy make some kind of weighted least squares, nonlinear least squares fit of these components, and then use this. Problem of all this is to get really insight in the analytical behavior. You have to simulate a huge amount of times to get some, and still to get some appropriate results. Simulate some
doing
more
a clinical trial.
So, and on your comment with the distribution assumptions, I think here in this talk, I would say everything was relatively based here on the true model, which is stated here, for example. But you're right. In the point when I do the approximations, I'm for sure leaving this all of these things. But when I transform something, it was here with this function g of beta or something like this, I'm sure that I have to. I know that I have to keep in mind which distribution I had earlier, and I have to, in this way, to transform my nonlinear model in which I am doing everything. That's right. Yes.
Okay, more questions?
Yes, I have two questions. First, for M4, you gave us a solution, the formula with an E. How did you do it? How did you implement it M4? Because you still have an expectation in M4. So you simulation,
I
just Monte Carlo simulation to get M4?
Yes, that's all I did.
Okay, so you just
So
sample.
I think it will probably in some other models will get some totally unreasonable results.
Why?
Don't know. I think I had sometimes 2 years ago or something. I tried it already, and I had a bad example then, and I wasn't looking at it anymore. And just 3 weeks ago, I just started again looking at it and thought,
Because here
maybe
it
not
says-
that bad. But
And the other question is about the simulated Fisher information. Is it because you did empirical Fisher metrics, so you simulated data set, fit them, and so on, or it's really a stochastic approximation of the Fisher information?
I would say it's a really stochastic approximation. What I do, in fact, is I approximate.
Which approximation did you use?
I approximate this integral, this expectation by approximating some observations yi. Then I take some new approximation, some new normally distributed, pseudo-normally distributed random variables, and I compute their conditional mean, and then I compute the variance of the conditional mean and something like this. So I would say that's a stochastic approximation.
It's real Monte Carlo.
Real Monte
Yeah,
Carlo,
yeah,
yes. It's not more than this.
Valeri?
Actually, I want to compliment what was said by Professor Bates, actually. You see, we are going, and maybe it's a good way for you to explore. You have all machinery already. So what we are doing right now, what you described, so you work with information matrix, but what if, and then you try to verify what kind of approximation, good, bad, or whatever. And what is important and what I like actually what you have done, you also look for designs. So how they vary under different assumptions. But now let's start a little bit earlier when everything is simpler. For instance, in PK modeling, they always assume the parameters, logarithm of them, are normally distributed. Okay? And now you jump from there 400 kilometers ahead, so doing all these simulations and approximation. What we change, say, we can transform parameter theta, say, to some kind of area, not with log, but I can use any other function, which will also transform parameters to be always say. I know that parameters positive, but why to take log? There are a lot of other elementary functions which do mapping to minus infinity, plus infinity, and assume that it will be normal. How it will change my optimal design, even for any simple approximation. Maybe it will be stronger effect. And we are fighting, you see, with something which could be, actually you show mostly minor changes, when, as was correctly noted, so we have to start earlier to really to see what happens if. And I think reparameterization is very important here, because it could be more important at earlier stages.
That's right, but what I just think about is what we in fact have somewhere here is we have these penalized sum of squares where we have where we take c squared deviance of the observations from the response functions, and we have here this difference of the.
This term could be quite different. You see.
In fact, yeah, that's right. But in this model with the log, for example, then you transform, and then you have here the log of beta. So you have your bi transpose d inverse bi or something like this. If you.
And another thing, do we have?
I think it's
Make it quick, please.
No, I don't want that. Okay, so everyone concerned with information matrix which to some extent is asymptotic value for variance covariance matrix of your estimated parameters. But actually in this mixed effect models, if you start to do everything based on Taylor expansion, so if you start to do Taylor expansion for your response function, then the second term appears, is biased, so which depends upon second derivative. And why not to consider these two elements together? Because that is important. Our total MSE, what they call them, mean square error,
Yes.
is important. Not only variance, but MSE. And nobody talks about this. And I think it could be, at least I didn't hear it.
You know, if we would have some more insight in these estimators for some small data sets, so if we have, I think then we might really good design our experiments without using this Fisher information which we can't compute. So maybe it would be better to look at the variance of some more robust estimators to get them.
But still,
This is
we
what
have
we're
to
looking
look
for.
not only at variance, but at MSE, really at MSE
Yes,
we do when we simulation. What I try to emphasize, we have to introduce MSE, and then it will be really reflect what is needed. Especially this MSE could be big in the area which probably of the most interest in PK modeling, in the area of maximum of your curve. Because their second derivative could be very influential.
Okay, so let's continue with the session, and first